4.3 Part 2, connecting f prime and f double prime with the graph of f. Your objectives for this lesson are to determine whether a graph is concave up or concave down, to locate points of inflection, and to use derivatives to describe the graph of a function. Let's look at the definition of concavity. So the graph of a differentiable function, y equals f of x, is concave up on an open interval I if y prime is increasing on I. So the slope of your derivative is positive. And concave down on an open interval I if y prime is decreasing on I. So if your slope of your derivative is decreasing or negative. The concavity test. The graph of a twice differentiable function, that means you can take the second derivative, is concave up on any interval where y double prime, or the second derivative, is greater than 0, and concave down on any interval where y double prime is less than 0. Example 3. The curve y equals x squared is concave up on negative infinity, comma infinity, so everywhere, because its second derivative, y double prime, is always positive. Let's look at a graph of this function so that you can see what I mean here. So y equals x squared. Okay, and you can see here that the function is like a cup, and that is basically what concave up is. This is a perfect example of concave up. So when it's a cup holding water, it's concave up. If this was turned the other way, like all the water would fall out, then you have concave down. So, and you find this by looking at the second derivative. So the first derivative of this would be 2x. The second derivative is 2. You see that 2 is always above the line y equals x. It's always positive. And that indicates that this function is concave up 100% of the time. Okay, example 4. Determine the concavity of y equals 3 plus sine x on the interval 0, 2 pi. Let's start by finding the second derivative. So y prime, the first derivative, is going to be cosine x. Y double prime is then negative sine x. Graphing negative sine x. Okay, so I have, well, sine x would start here at 0, 0, so we're graphing it upside down to 2 pi. And 1 and negative 1. So I'm going to have a point here at pi over 2, comma negative 1. Okay. So this is negative sine x, but with a smoother curve. It's good enough to see the sign though, which is what we really need. So I can see from 0 to pi, negative sine x is negative, which means that my graph here will be concave down. So concave down on the interval 0 to pi. This is because y double prime is negative. Okay. And then over here, I can see my graph is positive. That's from pi to 2 pi. So my original graph will be concave up from pi to 2 pi, and that's where y double prime is positive. That is all I need for that problem. Okay. This brings us to the idea of a point of inflection. So definition of point of inflection is a point where the graph of a function has a tangent line and where the concavity changes. So that is a point of inflection. So at such points, y double prime is either 0 or undefined. And if y is a twice differentiable function, y double prime equals 0 at a point of inflection, and y prime has a local max or min. So where the second derivative is 0, the first derivative has a max or min, and the original function has a point of inflection. Example 5. A particle is moving along a horizontal line with the position function s of t equals 2t cubed minus 14t squared plus 22t minus 5, so long as t is greater than or equal to 0. Find the velocity and acceleration and describe the motion of the particle. Okay, well this first part is easy, finding velocity. I know that velocity is the derivative of position, so s prime. So I'm going to have 6t squared minus 28t plus 22. Okay. And I'm going to go ahead and factor this now to make my life a little bit easier later. So I see a common factor of 2 among all of these. So I have 2 times 3t squared minus 14t plus 11. And I can factor this trinomial a little bit more. So I'm going to have t and 3t to give me 3t squared. And I'm definitely going to have a 1 and an 11. Let me try this combination first. And if it doesn't work, I'm going to switch them. So this would give me 3t. This is 11t. Oh, good. So since both signs are negative, those add to 14t. I'm all set. Okay. So I'm going to leave my derivative like this. Now, acceleration is the derivative of velocity. And I'm going to use this top line to find the acceleration. So 6 times 2 is 12t minus 28. Okay, and again I'm going to factor, so they have a GCF of 4. That's 3t minus 7 left. Okay. Next thing we have to do is describe the motion of the particle. I know already, so if I was looking at this graph, it would be something cubic, like that-ish. So when I'm moving up on this graph, so increasing, my particle is moving to the right. So s of t increasing means I'm moving right. And when s of t is decreasing, so like in this part here, it's moving to the left. I can figure out exactly when it's moving left and right if I look at when my first derivative is equal to 0. So setting this equal to 0, I'm actually just going to set each factor equal to 0, and that's already factored. So t minus 1 gives me t equals 1. 3t minus 11 gives me t is 11 thirds. Okay, so those are my times when I am changing direction. So changing direction. Well, let's see which direction I'm actually moving in. So I'm going to bring back the sign chart. So I'm going to have my intervals first. I know the first one is going to be from 0 to 1. And then from 1 to 11/3. And then 11/3 to the end of time. Okay. And I want to know the sign of s prime, so the sign of my velocity. Then I want to know behavior of s and my particle motion. Okay. So I'm going to plug in right here, I guess 1/2 into my factored version. So copy this. Okay. If I plug in a 1/2, this will be negative in here. So I have a negative times this 2 is positive. And this would be negative also. So I have negative times negative is a positive times positive, so this will be positive. Okay. If I plugged in, I don't know, if I plug in a 2 here, so 2 is between these two values here. So this t is 1/2. T equals 2. I'm going to have 2, which is positive, times 2 minus 1 is positive. 2 times 3 is 6, minus 11 is negative. So plus plus minus gives me a negative. And if I plugged in a 5 here, so t equals 5, I'm going to have a positive for the 2. 5 minus 1 is a positive, and 15 minus 11 is positive, so this will be a positive. So that means that S is increasing, decreasing, increasing. So I'm going to move right, left, right. So between 0 and 1 second, my particle is moving to the right. Then between 1 second and 11/3 seconds, I'm moving to the left. And after 11/3 seconds, I'm moving to the right again. Okay, now let's look at the second derivative, acceleration. So when that equals 0 is when I'm going to have my points of inflection. So let's set 4 times 3t minus 7 equal to 0. So basically 4 is never going to equal 0. 3t minus 7 equals 0 when t equals 7/3. So this is my point of inflection. So my sign chart here, don't worry, we still get one, is for 0 is less than t is less than 7/3, and then 4t is greater than 7/3. And I want to know the sign of A, which is S double prime, and what the graph is doing. So graph of S. Okay. So let's plug in a 1 for this first interval. And if I plug in a 1, what was my function? 4 times 3t minus 7. Yeah, okay. So if I plug in a 1 here, I get positive 4 times a negative. So this is a negative. If I plug in t equals 10, which is greater than 7/3, I get positive times positive. So this is a positive, which means over here I'm concave down, and here I'm concave up. If you were to interpret this in terms of the particle problem, that means that the accelerating force, whatever it may be, directed toward the left, so it is directed towards the left during the time 0 to 7/3 seconds, so over here, because negative means left, and towards the right when it's time greater than 7/3 seconds. When you reach t equals 7/3, that accelerating force is equal to 0 for the shortest, briefest moment possible. And that is the end of part 2.